So the next section of Mastering Astronomy deals with the heliocentric model of the solar system. This is 2.3, and as the name, as the name implies, heliocentric, helios for sun, centric, center. This is kind of giving rise to our current model of our solar system. At the time this was developed, our knowledge of the entire universe was really limited to just our solar system. So we've built upon this, but this is just our baby steps here. So what we see here in this picture is showing that if the sun is at the center, and we've got the Earth, and beyond Earth is Mars, we get a way to explain that retrograde motion of the planets there. So here we've got the actual position of Mars and Earth at these different points, but if we draw a line through them and we look at the background stars, we're going to see the apparent motion of Mars moving backwards and then back on its forward course through the sky at different times during the year. So this was one piece of evidence that the sun was the center and the planets that orbited it. This took away a lot of the complexity of Ptolemy's model that had the orbits of the planets going around the Earth, and those orbits of the planets had little orbits upon them, or epicycles on top of the original orbit, or definits. So this is really the start of the Copernican revolution. These little 7 points here are just really showing us the main ideas of what happened at this time. So this is, again, the 1400s, 1500s, 1600s, putting Earth no longer at the center of everything. The second one here is not still true today. It never was true, but we just, Copernicus thought that the moon orbited the Earth, and the Earth was at the center of the orbit. Turns out they kind of orbit each other, where the center of the moon's orbit and the Earth's orbit is somewhere a little bit below the Earth's crust. So it's still within the Earth, but looking down from above at the motion of the Earth and the moon, the Earth has a little bit of a wobble to it, but they didn't realize this at the time. All planets are going to go around the sun. The stars are much, much further away than the sun. The motion of the stars around the Earth is due to the Earth rotating, as well as the movement of the sun around the Earth, also due to the Earth's rotation. And then the retrograde motion of the planets that we saw is due to the fact that Earth and those planets are going around the sun at different speeds and in orbits that are different sizes. So it gives us that apparent change in direction as the Earth overtakes other planets in their orbits. So we can kind of credit modern astronomy to the likes of Copernicus and Kepler and Tycho Brahe, but I think many people would agree the first real scientific-minded astronomer was Galileo. So Galileo used the newly invented telescope. He did not invent it, but he really was one of the first to turn it to the skies to take a look at what's going on. So we knew planets at the time. We didn't know what planets were. We just thought they were these objects in the sky that really no different than stars, but would just move in different directions in relationship to the stars. So Galileo took this telescope that he made, took glass and ground it to the right shape to magnify the image, and he looked at Jupiter through a telescope. And to the right here, on this diagram, shows his observations on different nights. And these little asterisks here, these represent what we today know as the moons of Jupiter. And by keeping close observation of this, he could figure out that these were actually in orbit around Jupiter. So this really kind of puts a nail in the coffin that everything, of the idea that everything orbits the Earth. Here we have proof that objects are orbiting in another body. So here's Jupiter being orbited by moons. He also used this telescope to look at the moon. And he found that the moon wasn't this perfect, spherical, smooth object that we thought it was. It had mountain ranges like on Earth. It had valleys, these huge craters. Definitely a far from perfect surface. Same day with the sun. Doesn't have mountains or anything like that, but the sun has sunspots, and he recorded many of these sunspots by looking at the sun through the telescope. Definitely not something you want to try at home. Easy way to go blind. And then the other issue that he saw was that Venus has phases. So if you look at Venus through a telescope, you'll see that sometimes it has a crescent shape, sometimes it has a gibbous shape. And this can't be explained unless Earth is at the center. I'm sorry, unless the sun is at the center, Venus and Earth are both going around the sun. If we look at this top picture here, this is the heliocentric model of the solar system. When we are orbiting the sun and Venus is orbiting around the sun, we view Venus through a telescope and we'll see sometimes Venus looks like a quarter moon. Sometimes it has a crescent shape. And that can be attributed to the fact that the orbit of Venus lies interior to the orbit of Earth. If we look at the Earth center solar system, there's really no way to see the phases that we're seeing if we put the sun at the center. So we can't really explain it with the geocentric model. So just from Galileo's observations, we have 4 pieces of evidence that puts the Earth firmly at in orbit around the sun. And this is quite a few decades after Copernicus. So just because Copernicus kind of came up with a notion doesn't mean it was widely accepted. More and more evidence led to our current belief and our understanding of the way that the solar system is put together. So Kepler, working with Tycho Brahe had this really incredible observatory for the time. Today we think of observatories as having telescopes. They didn't really have telescopes, but he had this long kind of rod that was, it could be changed. It could be changed which direction it's pointing. It could be changed which its angle with the horizon. And based on those and the timing at which these objects were sighted, he could really make accurate records of where these planets and stars crossed the meridian, when they rose, when they set. And he just kept fastidious records. So Johannes Kepler, worked with Tycho Brahe. You couldn't really get more different, 2 less similar people working together. But Kepler was really, really good at math and seeing connections that weren't necessarily obvious to Tycho or others. And this led to his 3 laws of planetary motion, Kepler's. So the first law is that orbits aren't perfect circles. These orbits are ellipses, and kind of like what we drew in class on the whiteboard, you take 2 points and a string and stretch it between those 2 points and make that line between the string taut. You draw all around this, you're going to end up with an ellipse. And this ellipse has what we call a major axis, and there's a minor axis, which is less important. But here's our semi-major axis. So half semi, like a semester, half of an axis, we call it a semi-major axis. So the longest axis is the major axis. One of these 2 focuses, or foci, I forget which the proper pronunciation, will always be the sun. And all the planets will have the sun as one of their focal points. And then the other one is just, it's different for all the planets. So it's just a spot out in space. The second law is called the law of equal areas. So if we imagine a line that connects the planet to the sun, that if we look at the area that line sweeps out over a set amount of time, that's going to equal the same area regardless of where we draw that line. So suppose we'll just call this a month. This red arrow represents 30 days, regardless if it's right here, or if it's right here, or if it's right here. The arc, or the triangle swept out by this, is going to have the same area as long as we're looking at the same amount of time. And for that to be true, the farther away a planet is, the slower it has to be going to the sun. So you can think of the planet as falling towards the sun. As it's falling, it's picking up speed. It's flung around the sun. As it's going away from the sun, it's being slowed down because it's being pulled by the sun's gravity. And then we do it again. So the planet's moving the fastest when it's around, close to the sun, moving the slowest when it's farthest from the sun. And then the third law of planetary motion, Kepler's third law, said that the square of the period of the planet's orbital motion, meaning basically the square of the length of a year in Earth years, is proportional to the cube of its semi-major axis. So essentially the distance from the planet to the star, if we take that cube. So for all the planets that we have in our solar system, if we look at our distance from the sun and we look at the time it takes to go around the sun, we can use the formula p squared, period, or time, over a for the axis, the distance from the sun, we're going to end up with nearly 1. Now, we got slight differences, mainly because we're dealing with numbers that aren't perfect circles. But for the most part, within hundredths of a unit here. So Kepler's third law really holds true for the objects in our solar system and in solar systems outside of our sun-centered solar system. So if we look at this, this will be our last slide. If we look at this diagram here, this is greatly exaggerated. In reality, the sun and the other focus are much closer to the center, but if we look at our major axis, we've got a couple of key points on here. When the Earth, or whatever planet is closest to the sun, we say it's at perihelion, helion for sun, and when it's furthest away, it's at its aphelion. So the farthest. Apogee is when the moon is furthest from the Earth, and perigee is when the moon is closest to the Earth. So we use that ap for far and para for close. So that'll stop it for now.